After watching this video, you will know how to design and estimate EMI electromagnetic interference filter by simulation in LTspice. Let us start and have a successful day with EMC. The classic way to test filters in reality can be seen in the example of a sinusoidal source of known amplitude and variable frequency in a 50 ohm system with source impedance and load impedance 50 ohm. For each frequency we will plot the insertion loss in dB, which is equal to 20 log times voltage without the filter divided to the voltage with the filter. This is voltage with the filter and this is voltage without the filter. And the graphs will show the attenuation of the filter in the measured frequency range, but also the gain amplification that we want to avoid or even need to avoid. This is not a realistic test circuit. It may be easier to measure in reality, but in terms of simulation we can try a different approach with more realistic impedances that we'll have in the test circuit when we use LISN, line impedance stabilization network. Also, common mode and differential mode current have the source impedance of the SMP input with parasitics, but the load impedance is the LISN impedance. The value of it depends on the type of noise source and its current flow path. So let's see how to simulate a common part of the input filter. This is a simulation of common part of the mains input filter. I prepared 4 circuits. First, our reference circuit without the filter. Second, with ideal filter components. Third, circuit with vendor model that contains parasitics. And last circuit with additional wire parasitics. For the common mode, in the conducted emission test setup, for example, test setup that you saw in part 1 of this series, the current from the source will flow through both conductors to the leading impedance, then to the reference plane, back through the parasitic capacitance to the source. The impedance seen by the noise source will be 25 ohm because the current from the source will split symmetrically. This impedance will affect the performance of our filter, since the insertion loss of a given filter depends on the impedance of the source and the load. That using the insertion loss graph provided by the manufacturer to evaluate the performance of the filter in a product may not give realistic results. And also one of these resistors will be termination resistor and the other the impedance of the spectrum analyzer. That depends which line is being measured at given time. Second circuit consists of CY capacitors connected to the ground reference, and these capacitors are safety capacitors that will open in case of failure to protect user of the device from short circuit. Further, we have coupled inductors with windings starting from this same side. These coupled inductors are called common mode choke. These provide high inductance for common mode current and much less for differential mode current as a leakage inductance. Typically, leakage inductance will be 0.5 to 5% of the common mode inductance. So 1% will be 1 micro Henry. But for simplicity, I draw this circuit that we don't have any leakage inductance because coupling coefficient K is 1. And this is a more realistic approach. With the vendor models, you need to download or create models by yourself. These are Rode-Schwarz models of 2.2 nanofarad capacitors and 1 millihenry common mode choke for mains input, and this is show us more realistic results, but we are lacking something here. We don't have parasitics that are between our components. So one of these parasitics will be wires, our wires between the lead-in and our filter. So here we will be having a connector to our device, and here we'll be having a connector to the lead-in. And in between we'll have maximum 1 meter cable. And parasitics of this cable, series resistance and series inductance. These values could be lower even because I didn't include a mutual inductance. So let us see the results. Press run. Here are results. Let's see here. Typically insertion loss have positive values, not negative values, but I flip the voltages that we are dividing by voltage without filter. In this way we have any value going under 0 dB is attenuation and above 0 dB is amplification of voltage. I think this is easier to evaluate and understand. So let's see our results for ideal filter. We can see that our resonance point 1 divided by 2 pi square root of LC is lower than our real values. That is because we have higher value of capacitors, and we also can see that we don't have too much resistance. That is why we have very high Q factor, and what we want to avoid this peak value, and we can do that by adding resistance to our circuit or shift it in a lower value when we don't have our limits. But for common mode we are mostly interested in the values above 1 MHz, because we have these parasitic capacitors that have 500 picofarads, and noise will couple through this parasitic capacitance above 1 MHz. It can be lower value. You need to estimate how much capacitance you have in your voltage. Typically it can be between 50 picofarad to 500 picofarads. That depends on your device. And what we can see that between, let's see, 1 megahertz and 30 megahertz, we have 50 dB of attenuation and 100 dB. This is a lot. This is good value, but this is ideal filter. So with the vendor filter where we have parasitics, our capacitance resonance will be have higher values. Of 26 dB attenuation and having on the end 54. So how much attenuation we want to have? Let us compare our attenuation to the graph from the first part of this series, where we have amplitude above our limit lines. Let us see results from previous part. Here above 1 MHz we need around 5, 10, 15 dB at least, and around above the 20 MHz we need 5, 10, 15, so good value will be 20 dB because we need to include our parasitics that will lower or damp if we have them more, resistance, for example. For the circuit with cable parasitics, we have minus 26, minus 54. So this same. So these 1 meter cables are not influencing our results in the conducted emission bandwidth. And this will be all for conducted mode simulation that we need to do. Our 1 millihenry common mode choke and two capacitors 2.2 nanofarad will be enough to dump the graph that we saw in the first part of this series. Let us see now how to design differential mode noise part of the mains filter. For the differential mode part of the input filter, I prepared 5 circuits. First, our reference circuit without the filter. Second, with ideal filter components. Third, with real vendor models. Fourth, with input cable parasitics. And fifth, final one, with our input capacitors that will be close to our switch mode power supply, additional differential mode inductors, and the resistor that will discharge the input capacitor. Let's see our reference circuit first. For the differential mode in the conducted emission test setup, the noise current will flow from our source through plus high potential wire through both resistors in Leiden, one from termination and second from the spectrum analyzer, to our minus return reference wire to the source. And what you need to know that in case of differential mode, the source is low impedance and the listening is high impedance. That's why in the filter circuits, you need to have high impedance components on the low impedance source side and low impedance components on the high impedance listening side. That will give you a well working circuit. As you can see that we have differential mode inductance simulated by two inductors. I will show you the results why we have two inductors here. And we have 6 capacitor, so again safety capacitor, but in CX class, 2.2 microfarad. Going in real vendor models, we have common mode choke that we used previously in common mode filter part. We will use its leakage inductance as a differential mode inductance. We will check how much of this inductance we have. And we have our CX capacitor 2.2 microfarad. Both components are from Rode-Schwarz website. And the last circuit is circuit with cable parasitics, but also with our input trace inductance and our input capacitors for SMPS that we will have in our device. We have 3 types of capacitors, and we will see how these capacitors influence our results, and also because our differential mode attenuation will be not enough, we have 2 additional differential mode inductors that we'll use to increase our attenuation. Let's see the results. We have our ideal graph, our vendor models, our cable model, and our parasitic with cable and input filters. Let's start with ideal model in correspond to vendor model. What you can do here is check how much leakage inductors provide the model of the common mode choke. So let us check that. So I can delete this inductor, put a wire here, press run, And as you can see, we have a mismatch between the graphs and our resonant points. So we can increase the inductance in the ideal model to see how much inductance we need to add and how much differential mode inductance we have in the common mode choke. If we add, for example, 2 microhenries, we can see that we are much closer now. But we can see that it's still not enough. We can add more, for example, up to 6 microhenries. And now we can see that our graphs are almost identical in this part, and our resonance points are very close to each other. So we can say we have around 7 microhenry of differential mode inductance and 2.2 microfarad capacitor. And we can check how much differential mode attenuation we have between 150K and 30 megahertz. Say that we have from -20 to -60. But for the conducted emission, we are mostly interested in the low frequency part of the graph. So between 150 kilohertz to 1 megahertz, we should have the highest differential mode emission. And we can check that for the graphs that we saw before with conducted emission above the limit. As you can see, from the 150 kilohertz, we are 5, 10 dB above the limits, but you need to also include derating of your components. So inductors for higher current will have less inductance, and capacitors also derating with the voltage. So we need to have some higher attenuation to include derating. So for example, we have -20 dB. That could be not enough, and we should include more attenuation. And we can do that by adding more inductance. So next, we let out the cables influence our conductor differential mode. So we have slightly more attenuation for higher frequencies, but we need to think in the region from 150K to 1 MHz especially. Next, if we include our input capacitors and wires, we can see different results. Let me, for a moment, let me delete the inductors. And again, let's see the result between the 500 kilohertz to 30 megahertz. We have a little bit more attenuation, but we have also amplification, but in the higher frequency region. For conducted emission, it will be not a problem. For radiated emission, it could be a problem. What we can do to increase even more our differential mode inductance, we can add inductance in series with our common mode choke, and this inductance should be split on both wires. Let's say you want 200 microhenry inductance, then you need to add 100 microhenry for one line inductor and second inductor 100 microhenry for second line. That is important to have inductance of both lines because each of the line is measured. So let's see our result now with the inductance added in the conducted emission bandwidth. We can see that our attenuation increased about 30 dB. 30 dB at 150 kilohertz. That is a lot. And then we have more attenuation also at the 1 MHz. Next, let's see our final filter checked for common mode and differential mode. This is our final filter simulation. We will check our filter with all the components for common mode and differential mode. And let's see the results. You can see that our common mode part of the graph is influenced by additional inductance in the equations, and our differential mode is also influenced because we have these two capacitors, CY capacitors, and we connected our one differential mode line and second differential mode line by two capacitors in series. Let us have a closer look in the conducted emission bandwidth. We can see that we have some attenuation of conductive current from 150 kHz, and at 1 MHz we have a resonance peak that is not so good because we can have some amount of conducted noise here, and we are close to 0 dB, so no attenuation at all. These could be checked by additional measurements if we need more attenuation at this frequency. Further, we have a lot of attenuation, and we are going to minus 100 dB, and then a little bit higher, around minus 60 dB. You need to include also derating of your component. So sometimes models can have derating in them, but actually sometimes you need to create components with derating. You need to create components with lower values as it would be in reality. And for differential mode between 150 kHz and 1 MHz, we have amount of attenuation that should be enough, including derating. That is all for conducted emission filter simulations. In the next part, I will talk about how to estimate the noise that we will have in a specific bandwidth for conducted emission and radiated emission, how much amplitude versus frequency you will have, and how the graph will look for the noise source that we will have. What parameters influence your noise? See you then. Bye.